So in thinking about two-source interference, what we want to do is we want to talk about what kind of patterns the two-source interference can give us. So I've got two sources here that are represented by these two dots. So a source on the left and a source on the right. And again, I'm going to let them emit identical waves that are in phase with each other. And so part of what I want to think about is, well, what patterns do I start to see if I think about what's going on along some line that I walk that happens to be parallel to the line that connects my two sources? Just to be clear in this pattern is, let's let the red circles identify peaks in the pattern, and we'll let the blues identify troughs. So part of what that's going to do is it's going to let me figure out where it is that I have two peaks interacting, which I know is going to give me constructive interference, and where I have a peak and a trough interacting that's going to give me destructive interference. And so the first place I can look is along this center line. And what I see here is I've got red circles overlapping, blue circles overlapping, red circles, blue circles. So what I see is this is a line of constructive interference. It also happens to be the point where the distance that each wave has traveled from its source is identical. So in saying that this is the point where we have the minimum path difference, what we're pointing out is that the path difference along this line, which basically runs along the center line between the two sources, it's perpendicular to the line that connects them, that the path difference here is 0. This line gives me the maximum. The line that connects my sources is going to be the largest path difference I possibly have, because for any point along this line, the path difference from the wave traveling from one source or the other is simply the distance that separates my two sources. So I can have path difference that has values from 0, because you lie along this line, all the way up to whatever the distance that separates my sources is, because then you're along this line. Well, again, as we start to look at what we see within this pattern, we said that along the center line, where the path difference is 0, we're going to get constructive interference. If you look just to the side of that, what you'll see on either side is a line where you have red peaks crossing over blue troughs. But you see, anywhere along these dotted lines, my two waves are canceling out. And that's true on both sides of that center line. That both of these represent the first point where my waves cancel out, which corresponds to a path difference of 1/2 wavelength relative to the other. So pick any point along this line, and we can say that, oh, from source 1, when I look at this point here, it has traveled 1 full wavelength, 2 full wavelengths, 3 full wavelengths, 4 full wavelengths to get to that point. From source 2, it's traveled 1 full wavelength, 2 full wavelengths, 3 full wavelengths, 4 full wavelengths, and an additional half. So it's traveled an additional half wavelength from source 2 than it did from source 1. If you flip over and look on this side, it's traveled that additional half wavelength from source 1 than it did from source 2. So we have this initial line of constructive interference, then these two lines on either side of destructive interference corresponding to 1/2 wavelength of a path difference. Next, I can find a constructive line that corresponds to path differences of a full wavelength. So here again, when I look, I see red overlapping red, blue overlapping blue. And so again, just given a particular point, at this particular point, let's say the wave from source 1 has traveled 1-2 wavelengths, which tells me that the wave from source 3 will have traveled 1-2-3 wavelengths. It's traveled 1 wavelength more. I can keep going out, and again, now I'm going to run across a line of destructive interference that corresponds to a path difference of 1.5 wavelengths. Keep going till I see a path difference of 2 wavelengths, which gives me my next constructive interference line. A line that gives me the next destructive interference that corresponds to path differences of 2.5 wavelengths, I can keep finding these lines of constructive and destructive interference until I get to the point where I need a path difference that is larger than the distance of separation. Because again, remember that the distance of separation always gives me my maximum possible path difference. So in this case, it looks like we are almost, but not quite, getting to that next line where the path difference is 3 wavelengths, so another line of constructive interference, which tells me that my two sources are separated by a distance that's just less than 3 wavelengths of the waves that they're emitting. One way to visualize this is in terms of thinking about what happens with light. We can create these patterns with light where what you see are bright and dark fringes. Now, light waves obviously aren't mechanical waves, but the pattern we're able to see with light waves is exactly the same as the pattern that's there when we use mechanical waves. So when we're dealing with something like sound, we can't see that pattern, but we can detect it, and it looks like what we see when we do this with light. You get a pattern that has alternating bright and dark fringes. So the bright red are the bright fringes, the black are dark fringes, and so these bright fringes are where we have constructive interference. The darkest black is where we have destructive interference. And so you can think about, well, this is the path difference of 0, half a wavelength, 1 wavelength, 1.5 wavelengths, 2 wavelengths, 2.5 wavelengths, 3 wavelengths. So here's our pattern represented with light waves. We could get that same pattern using sound waves if you started from a point right along the center line and simply started walking off in this direction. If you had a detector that lets you detect the two sounds coming from each of these sources. So what your detector would see is, well, here's a point where you'd get a really loud signal. But as you started walking this way, the sound would drop off until a point where you got no signal at all. If you kept walking, your signal would start to come back, and here again it would be really loud because you're back on a bright fringe. You're back at the point where you get constructive interference because the wave from source 1 is traveling 1 full wavelength longer than the wave from source 2. But in traveling 1 full wavelength longer, it means that they're back in phase with each other, and so your signal is really strong. Keep going, your signal drops off again until you get to the next point of destructive interference where you don't get any signal at all. And of course, here's where the wave from source 1 has traveled 1.5 wavelengths longer than the wave from source 2. So this pattern that we can see using light waves, we can hear by walking with a detector that lets us detect sound.